Let's get started. And I saw many of you last month at WasmIO and KubeCon. So it's great to see you guys again. And since we just came back from KubeCon, we heard it loud and clear. There's great interest in AI and a great interest in running AI applications in Kubernetes, right? So in this month's talk, we had two talks, one beginning and one end, that are very specific to running AI applications, large language model applications in particular, in WasmEdge, in a Kubernetes or container environment, which I thought was very interesting because it represents two, I think, similar but very different approaches, and it shows there's lots of exploration that's going on in the community. And then in the talk in the middle, we're going to talk about running more traditional AI models. That's our project called WasmEdge. So people talk about how edge computing is important to our use cases, and we want to talk about computer vision and other things. That's to running very classic models like YOLO using WasmEdge. So yeah, so without further ado, let's introduce the first speaker. So Mr. Akihiro Suda is engineer at NTT, and he's a good friend, and has made, I think, very interesting and very important contribution to the WASM community. And he's also the maintainer of Llama, which is container runtime that's optimized for the Mac. So and he has contributed a project that could get around a lot of the issues with installing proprietary GPU drivers and things of that nature on the and run large language models on GPUs and hardware accelerators on a variety of different devices. So it's called WASI-NNRPC, or NNRPC. So I'll let him talk about the solution and give us a quick demo. Thank you.
Thank you. Should I share my screen?
Yeah, you should be able to share your screen. Yeah.
Hi, thank you. Can you see my screen?
Yes, it's great.
Thank you. Hi, I'm Akihiro Suda from NTT Corporation. Thank you for introducing me. And today I want to show demo of running Llama on Lima using WASI-NNRPC and WasmEdge. So first I want to introduce Lima. So Lima stands for Linux virtual machine, and this is optimized for running containers on macOS. And so this is really similar to Docker for Mac, but this is open source and optimized for functionality. And Lima also similar to Wave 2, but Lima is made for basically macOS host. And Lima supports automatic file system sharing and port forwarding. So the user experience is really similar to Docker for Mac and WSL2. And the default runtime is containerd, but you can also use Docker or Postman, and you can also use Kubernetes, and you can run Linux commands, including ZettaScale for running containerd with the commands like this. So you just run you install Llama to install Llama, and run llama-ctl start to start the virtual machine, and you can run Linux commands such as ZettaScale inside this Llama command. And Llama is made by utilizing QEMU or Apple's virtualization framework. But the problem is that these hypervisors do not support GPU. So there's a huge demand for GPU, but it's very hard to allow the virtual machine guest to use host GPU. So the workaround I'm proposing is to use WASI-NNRPC. So WASI-NN is an extension to WASI for using neural net, and WASI-NNRPC is a gRPC-based API for calling WASI-NN from remote machine. So we can use this RPC to use the host GPU from the Llama guest. And this is just a plain gRPC, so it can be also used from non-WASM applications as well. But basically, this is intended to be used from WASM applications. So RPC just looks like this. It's in the repository of WasmEdge, and we have a definition for tensor and API for loading graph and requesting computation of the graph like this. And there is an example application in github.com/techstate/WasmEdge example. And there is a WasmEdge GGMRPC.wasm. So you can access the remote WASI-NNRPC from this WASM application. So let me show the demo. So this terminal is the terminal on macOS, and this terminal is for the dimmer guest. So this is Linux, and this is macOS. And on the macOS, I'm running WASI-NNRPC server with this unique socket, WASI-NNRPC.sock, and Llama module is loaded to this server, and the client connects to this unique socket. So this socket is connected to the macOS host via SSH, and we can run this WasmEdge GGMRPC.was like this, and we can start with Llama. And the first execution takes some time for loading the model, and I'm using a very old Macintosh for this demo, so this takes time. But with the recent Macintosh, this should be much faster. And you can see that the model is returning this response. Hello, it's nice to meet you. I'm here to help answer any questions you may have, like this. So we can chat with the model, but currently there is no support for streaming. So it takes time to see the response. So we can't see any response until the model produces a complete answer. But in the future, it should be improved, and we should be able to get streaming for this chat. Yeah. So yeah, I asked where is the capital C of Japan, and it answers that the capital C is Tokyo. Yeah. So it's working.
Yeah. So well, I noticed you have you're running at about 2 tokens per second. I thought on the Mac GPU it should running faster than that.
Yeah,
So
right. So I'm using very old Macintosh. So this is Intel MacBook produced
okay.
4 years ago. Yeah, so this is very old, and this is very slow. But yeah, with
Yeah.
new Macintosh, it should be much faster. Yeah.
Yeah. That's so that's what I thought. I think the Apple Silicon you should get like 20 tokens per second, right? It's 10 times faster, right?
Yeah, right.
Okay. So that's very interesting. So that question I have is that the server is gRPC format. So in the WASM side, you have a gRPC library. Is that correct?
So the .wasm application doesn't care about the gRPC, because the WasmEdge itself has the support for gRPC.
Okay.
So WasM application just calls WASI-NN without RPC, and the WasmEdge runtime translates the WASI-NN core to gRPC core.
Oh, okay. That's cool. Yeah, that's so there's a question could gRPC's side potentially be leveraged to enable federated learning workloads? So I think I'll let Akihiro answer this question first. Do you think it's possible? The gRPC, you did an approach to enable federated learning applications.
So federated running, you mean? Sorry, I'm not sure.
Sorry, yeah. So my understanding is that federated learning application is that learning that happens on a distributed node, right? So you have a model training application that happens across different nodes. And my opinion is that in theory, this approach would fit well, because you would have one application that controls and talk to and potentially controls different nodes that do the training. However, WASI-NN is not really set up for training or learning. It's set up for inference. It needs a lot more, I think, functions in order for it to be able to support learning type of applications. So that's my understanding. So, but that's
Okay.
yeah. But I think this is a super interesting approach because that allows us to get around the whole GPU driver thing. Because one of the, as we'll see from the last talk from Vincent, and maybe from the next talk from Charles, is that to get GPC, to get GPU access in the container environment is a major effort and oftentimes requires non-open source software. So, so I think the approach that you took sort of get around the whole thing, which is really interesting. That's what you have demonstrated is that RPC running on the same machine, right? But it could run on a different machine. Is that correct?
Yeah. So you can just use a different thing. So it's just a unique socket. So yeah, you can just use any remote machine
Okay.
like running an instance on EC2 or any cloud.
Hmm. Yeah.
Yeah. But for federated running, we have to extend the protocol to support
Yes.
that. So because
Yes.
the current DRPC is just a plain wrapper with WASI-NN. So it's just corresponding to the V2X file. So this is just a translation of WASI-NN.V2X. So for supporting federated running, we have to extend upstream WASI-NN first, and then we have to extend the gRPC to support that feature.
Yeah, I think that's great. That's at least it's possible, right? It's a route that makes, if people do this work, it's possible for them to do that. Yeah. So, oh, that's great. Yeah, that's so we the other thing I really like it is because the inference especially in the large language model context, the inference happens much slower than the network. So moving everything through the network is not going to be causing any kind of performance bottleneck. So is another really good feature of this solution. So great. Yeah. So if there's other questions we can answer at the end of the talk. So thank you so much, Akihiro, and that's really appreciate all the work that you do
Thank
for
you.
the community. So excellent. So next up, we want to talk about running YOLO in WasmEdge. So this is one of our AIFX mentorship projects, and Mr. Charles Schleich, is that, hopefully I'm not mispronouncing your name. Yeah. So yeah, that's so because I just call you Charles, right? So he's living in Paris at this moment, so if I understand correctly, and so. Yeah, Charles has done a ton of work, enabling YOLO running in WasmEdge. That allows us to run in a variety of different new application use cases, which I'm really excited about. And so, yeah, let's, so I hand the screen next over to Charles and to demonstrate how to run YOLO in WasmEdge. Thank you.
Thank you very much, Michael. Can you hear me all right?
Yes, I can hear you all right. Yes.
Fantastic. All right. Okay, I'm going to start basically just with sharing my screen. And I don't blame you. My entire life, no one has been able to pronounce my surname, which is correctly pronounced Schleich. It's a very Schleich. Yeah, exactly. It's a German surname. To share my screen, let me see this one. This one. Right. Fantastic. We should have a little bit of screen sharing going. Can I just leave this all right over here? Okay, so I'm going to first and foremost thank you guys very much for letting me speak here. I'm going to give a more or less abridged version of my WasmEdge YOLO RS talk that I gave in Paris a couple of weeks ago, and we're going to kind of just get into it. Very short introduction. My name is Charles. I am mostly an engineer. I have experience with distributed systems, WASM, and Rust. I think we can really fly through the section on kind of WasmEdge runtime. I think everyone more or less knows how that works. So I think I'm going to skip over it because this is a community meeting for the WasmEdge runtime. And basically, I'm going to go specifically into the project that I did as part of the Linux Foundation mentorship. So a little bit of context. This was a project to allow YOLO models to basically to be pre and post processed. Let me rephrase that. It is the pre and post processing for the YOLO family of models. My implementation was specifically for YOLO v8. Different YOLO models have different input and output tensor requirements. So I just did it with the latest version at the time, which was YOLO v8. I see that YOLO v9 has been released. Yeah, basically that. It does not include any actual neural nets on my side, so I don't do any training. I only load in pre-trained weights, do the pre-processing of image and video files, and do the post-processing of image and video files. The project structure basically includes a WASM developer SDK, so specifically an SDK that is targeted at WASM binaries for the WasmEdge runtime, such that you can do image processing using the WASI-NN standard, as well as a WasmEdge video processing plugin. In order to enable video, I went the route of using FFmpeg as basically the underlying library to load video, to split out frames, to recombine video. So that's basically the very high level product structure. It is on GitHub, and I'm going to give this a very big caveat. It is still a work in progress. You can play around with it. There are things that are going to be broken, and the setup isn't entirely complete. I'm working on getting it to be in a more complete developer friendly state, more kind of developer experience state. I've just had a lot on my plate with work and university lately, so I haven't had as much time as I wanted to actually dedicate to the open source community, which is more time is coming up very soon as things calm down. Very high level overview as to how this talk and how basically the workflow basically goes is that the load image and the pre-processing I do, the forward pass through YOLO V8 is handled by WASI-NN, and then the post-processing of the results, as well as doing something with the inference, is something that I do, and the do something with inference is left to the developer at the end of the day. So let's start kind of high level with pre-processing, and I'm going to explain everything that I go through, because I'm not going to assume that everyone has knowledge with respect to image processing and basically, image processing and post-processing of the tensors. So I'm going to kind of go a little bit step by step. This might be a bit slow for some, it might be too fast for some, but I am going to try squeeze it into the 20 minutes that I have to speak. So the version 8 of YOLO, the 8th version of the YOLO family of computer vision models, expects a 640 by 640 image. It expects the aspect ratio of the original image to be maintained. So if you have a really large image, you don't want to just kind of fit it into that square. You want to actually scale it down and have a black bar somewhere. For instance, if it is a rectangle image, if it is already square image, then that's perfect. You can just scale it to the square. It expects a flat list of F32s in a specific format. And this is how we basically get through this format. So I got this image off of Reddit. It is a really nice computer setup, much better than the one that I own, courtesy of this Reddit user. The first thing that we want to do, and I hope that it's coming through all right on everyone's screen, is basically resize this image to fit in the square. You'll notice the black bar at the very bottom. It is maintaining the aspect ratio of the previous image, despite this awful animation between the two slides. We want to then split the image into channels, so it's RGB channels, and this is quite a nice image to kind of actually see how it's done, because you can see how much each color channel contributes to certain parts of the image, specifically around the lights being very overblown on the red channel, because obviously they contribute higher values than the blue or the green. Yeah, we basically split into channels, and we want to convert all of the values that we have for RGB into floating point numbers. So instead of just U8s, we're actually going to map those U8s onto F32s. We're going to flatten these into a single buffer of F32s, technically a buffer of buffer. So this is how the code goes from Rust. So now this is code that is part of the WASM library, the WASM SDK that I wrote for WasmEdge, basically. First thing we are basically doing is taking, let's see, did I actually do this well? Yeah, I did. First thing we're doing is we're basically going to find the longer side of the image, in the case that it's a rectangular image. Most images are rectangular images, and basically save the scale of this image. Next thing we are going to do, I'm sorry, I'm going to probably fly through this just a little bit. Next thing we are going to do is actually allocate a new 640 by 640 blank image. So just a black image here. And what we're going to do is actually copy the resized image that will fit into the bounds of a 640 by 640 image into the new buffer, which will allow us to have that black bar on one of the sides in the case that it is a rectangle image. Next thing we will do is split out our image into its individual channels, RG and B, which just involves iterating over every single pixel and grabbing out every single U8 value at every point in the image for each channel. Next thing we will do is actually flatten our image into a single RGB, into a single vector of F32. All right. If I'm not mistaken, I'm not going to make a comment on this. I think there might be a better way to actually write this double flatten collect, but for now it functions, and so we can make it even better later. Then final thing is we have basically this RGGBBBB image as well as some scale factor, which we are going to return from our pre-processing step. So that's effectively all that we do for our pre-processing. So next thing we do is pass it on to our neural net. So with respect to the neural net, I just want to double check. Can everyone see my screen still? I just want to make sure that something hasn't broken in between now and 5 minutes ago. Yeah, this looks positive. All right.
Oh, okay. Yeah, I can see it now.
Yeah, perfect. All right. So next thing that we're going to do is basically actually run through the neural net. Now, this is all very high level and doesn't actually involve crazy amounts of thinking, which is really nice on the developer. So we effectively in Rust. So remember, everything that we're doing here is in Rust. We're using the WASI-NN library. We are using an execution target, a graph, and a graph encoder. We're importing those three things from the WASI-NN library. We need to read a model file because we actually do need to have our neural net with trained weights existing somewhere and importing it into our runtime. We're building a graph. We need to tell it the type of graph encoding, the execution target. So for this project, I was actually only using a CPU specifically for the neural net stuff. We'll get into the video processing a little bit, but I only used a CPU for the neural net stuff in this project. In terms of using a GPU, it's actually quite nice because this execution target, you should be able to just change it to GPU if your runtime is built with GPU support, and voila, now it runs on a GPU almost kind of magically, which is really nice. And it's a nice implementation detail because it removes a lot of the whole setup and mental overhead from the developer, and actually also places a little bit more now necessarily on the DevOps person. So the developer can say, okay, I'm just actually going to develop the system, but I'm not going to worry about setting up GPU libraries and X and Y and Z. I'm just going to target a CPU for now. And then when we actually want to put it in production, we can just say, cool, actually now just use this on a GPU instead. And then the DevOps people will say, great, let's actually set up our environment such that we can run this on a GPU rather. So this is a really nice abstraction layer, basically. These are the two enums that we imported, graph encoding and execution targets, CPU, GPU, auto, as well as a number of different graph encodings. I actually might be wrong about this. I'm pretty sure safe tenses is also a type of graph encoding, but if someone could correct me, safe tenses is something that is an interesting project, and if I'm not mistaken, it is written in Rust. But don't quote me on that. I haven't actually checked that information very recently, so I could be wrong. The actual code for doing the forward pass through the network is super simple. We create a new graph with an execution context. We set our input, so we can have multiple inputs. We set our tensor type, which in this case was floats, F32s, which is what we formatted our image to be in the previous step. We set our input size. So this is basically going to be a slice of numbers, and this is what YOLO V8 expects. So a tensor of shape 1, 3, 640 by 640. And then we give it our tensor data, which in the previous step was our flattened vector of F32s. We have our output buffer, which we basically want to assign just zeros for now, of size the number of objects that we can detect in a single image and the number of classes. So in the case of YOLO V8, the number of objects that a single pass of YOLO or that a pass through YOLO V8 can detect is 8,400 objects in a single image, and the number of classes that it detects simultaneously is 80. And then we basically say, cool, compute this and get the output, and we pass it our output buffer, which is fairly simple. And I made nice animations to go through exactly this, and I completely ignored them for the second time presenting like this. So we have to do some post-processing now because we've gotten our result from the neural net. Let's have a look at how the post-processing is done. We have our vector of F32s. So this in the previous step, this is a vector of just F32s of a certain length. We need to take this single vector and actually format it into something that is a little bit easier to work with as a developer. So what we need to apply is a couple of different steps. The first one is basically non-maximal suppression, which basically looks at all of the different objects and suppresses the ones with low confidence scores and the ones that are not the highest confidence when making the detection. And then we need to do a reduce and intersection of union, because we're going to get in the neighborhood, when making a detection, multiple detections around an image with slightly different pixel bounds. And so what we actually want to do, instead of like taking all of them, because it might detect, for instance, let's say glasses, it might detect glasses in the rough neighborhood at like 100 different places with slightly different pixel bounds. We want to kind of take the overlap of all of those and the intersection over this union, basically the overlap with the maximum area, and just use the most likely, the one that covers the most area. So let's see how we do this. We can detect 8,400 objects, and we have 80 classes that we can detect from. So depending on how the neural net was trained, we can detect 80 different objects. And then we get basically the bounding box location for those different classes, or for the different detections, which is just x, y, width, and height. And that actually appears at the center of the image. And so in order to get the top left corner of the bounding box in the image, we need to just offset by half the width, half the height, and just do a subtraction. It's not so difficult. So let's have a look. A buffered to 2D array. First thing we basically do is start chunking this as, how did I do this? Yeah, so we basically start chunking this into 8,400 chunks, which allows us basically a window over our results, such that we can do a transpose into a format of 84 rows and 8,400 columns. Yeah, I think that kind of makes sense into a single vector of that. Yeah. So the output of this transpose is basically going to give us now all of our detections in rows, and our columns are going to match the format x1, y1, x, y, width, height, and then the probability of each detection. So detection 1 is going to be on row 1, detection 2 is in row 2, and so on and so forth, right? We need to apply non-maximal suppression. So what does this involve? First thing is we're going to skip over the first 4 numbers because those aren't detections, those are bounding box coordinates. We're going to get the maximum in the list. So we basically need to walk down that list on line 2 and find the highest probability of detections, get the position of this. We do a little bit of filtering here just to save on CPU cycles later on. So we have to give, as a programmer, as the developer, we're going to give some sort of confidence threshold. For instance, we don't really care if we're only 5% confident of some element. So if, for instance, we want to be quite safe, we can have like a 90% confidence or 95% confidence, depending on our application. And so that actually already removes a number of different results from our processing steps later. We find the most likely class in the possible classes. So 2 steps ago, we found the maximum number in each detection, or the maximum probability in each detection. And now we're going to actually find which class it corresponds to, right? So that just involves walking down the list and then corresponding it to the actual classes file that we also loaded in. So our inputs here are basically the image that we want to do the inference over, a weights file, and the classes that we're actually doing detection of, the list of classes. We do that offsetting that I was telling you about a little bit earlier, where the XY coordinates that we get are actually in the center of the image. And so we move left and up to get the up left corner. And then we push our results with the bounding box and the class to a list. And we're happy. We have our inference results. Okay, this is still in this repo. I need to clean up my slides clearly. We then apply intersection over union. So at a very high level, this is how you do the algorithm. You basically get the 2 bounding boxes, you find the area of both of the boxes, and then the intersection over that union. So we get the area of the intersection of those boxes, and we divide it by the area of both boxes minus the intersection. The reason I'm returning an option here is because if there is no intersection, we don't really care. Because these then our 2 bounding boxes, they don't really matter if they're completely different places in the image. Now, we can just kind of do this for every single pair of bounding boxes in the image. So this would correspond to every single detection. There is a vectorized version of this that I'm not going to go into the entire details of the vectorized version, just because there's some more interesting stuff about video processing a little bit later on, but you can go on to RoboFlow. This is effectively how I learned about this vectorized version. I translated effectively this NumPy code into Rust using, I think it was NDArray or NAlgebra, one of those libraries, to actually do the matrix multiplication. So it's also all open source and online. This article was written by a man by the name of Hitaskalski. I'm also probably saying that surname quite wrong. One of the interesting takeaways, and I'm not going to go through this entire vectorized version, although it isn't actually too long. One of the interesting takeaways that I got from this is between the NumPy version and the Rust version, NumPy does something very frustrating and silent in that when you are multiplying two matrices together, it will, and the matrices cannot be traditionally multiplied because their dimensions don't match. For instance, if you have a 1 by 90 matrix, a 1 by 90 vector, or matrix rather, and a 6 by 5 vector, you shouldn't, or 6 by 5 matrix, you shouldn't actually be able to multiply those two things together. And what will happen in NumPy is it will just silently extend the dimensions of one of the matrices such that it can multiply them together. It's very frustrating. And kind of one of the nice things about Rust is, or at least the library that I was using, is that it will explode and it'll say, I'm sorry, you can't actually do this. You have to explicitly say, I'm going to broadcast. So I'm going to extend the dimensions of one of these arrays. It was actually quite an interesting thing that I learned from both NumPy and now this Rust library. Yeah, so this is basically the output after we've done all of our non-maximal suppression and our intersection over union of that initial image that we put in. I think for fun, I'm going to, or I did rather, while we were sitting in the meeting earlier, my screen is still being shared, yes?
Yes.
So for fun, let me double check. Yes, I have took a screenshot of us just sitting in chat and I ran it through the neural net, so it actually does detect us all kind of at the top. Is my screen still being shared? Can you guys see this? So
Yes.
in terms of people, it picks up Michael as the most likely to be a person and Akihiro as the least likely to be a person. I'm sorry, Vincent, your face is just too high in the frame such that the actual output of the net it draws the text out of the frame, which isn't very useful. But yeah, this was fun. And then there's obviously no objects that it's been trained on in the screen sharing. But I thought that was fun. So in terms of the plugin interface, that all came through in your side, right? I can also run through it actually live. That would maybe be a little bit more impressive than me just showing this image of this processed thing. So in terms of actually the interface code, it's pretty simple. This is for the video because now what I just described was an image, and in order to handle video, it's effectively the same. It's just with many more frames. And so I'm going to describe a little bit of the interface to the YOLO RS video plugin that I did. And it's super simple. At the moment, it just handles files on the operating system. I would love it for one day for it to be able to handle video files that we pass in because semantically they should be pretty much the same thing. Although I'd need to look into how FFmpeg can actually handle in-memory files. I haven't actually looked into it. Time. Anyway, so one of the first things we do, this is all kind of like a more C-like interface, which is cool. However, it would be very nice one day to be able to pass nice types between the kind of WASM and plugin boundary. So now everything that I'm referring to here is basically the YOLO RS video plugin specifically, which was super, super fun writing because WasmEdge actually has some really nice documentation around the kind of Rust plugin SDK. So we basically start by loading the video into the host memory. So remember in WasmEdge, I'm just going to quickly go back through my slides a little bit. Inside WasmEdge, we have this WasmEdge runtime and we have our WASM executables running, and we can have multiple different plugins. Now, the WASM executables, if they are 32-bit, they are limited to 4 gigs of memory, whereas our plugins have as much memory as they need. I mean, unless you're running on a 32-bit system only, they have as much memory as 64 bits or 128 bits or whatever system that we can actually run this on. So they don't have the same memory constraints as the WASM applications, unless we have WASM applications that are 64-bit as well, which is quite nice because we can load in these huge videos should we want. So now, everything I'm talking about is, so this FFmpeg plugin, I kind of misnamed it here, is the plugin that I'm talking about when I talk about the YOLO RS video plugin. So let's just go back through here. So the interface code is quite simple. First thing we're going to do is load a video into the host memory. I'm passing a pointer here as well to get frame count. So this is called from the WASM application to the plugin. So the plugin, this function exists on the plugin, and the WASM application is going to call this with the arguments pass and load this video into your memory, please, with this expected size. Right? We have with these plugins are just such that I can write the WASM executable has knowledge of the dimensions of the images of this video, right? We have a get frame function, which just basically says get the next frame or get the frame of this index, which the WASM application is going to repeatedly call the plugin. Maybe there's a better way of doing this, but I got this one to work, so I was quite happy. Then basically the WASM executable is going to have access to this frame, which it is then going to pass through the entire workflow that we mentioned a little bit earlier of just pre-process, pass through neural net, post-process, and then we have our inferenced result, right? In the case, post-processing also involves actually drawing a bounding box and putting the little bit of text above the bounding box. Once we've done that, we can write frame back to the plugin memory, which we have its index, we have a buffer, and we have the length. And then once we've written all of our frames, we just do this in a loop. We have a function called assemble output frames to video, and it does exactly what it says in the tin. It assembles all of the frames. It then writes it out to a file by this name. So there's an example of one of my coworkers who tried to hide his identity by putting his hands over his face. I just recorded this on my phone and walked around a little bit the office. But yeah, this is basically it working on a video. Since then, I've been trying to upgrade the FFmpeg libraries on my machine and have run into some issue. When I was developing this thing, I was using FFmpeg version 4.4.2 on Ubuntu. I've been trying to use the latest version, which I think is version 5 or 6. I think it's 6. And so I need to basically play a little bit more around to get that working properly. Kind of go a little bit more into this because we are almost at the end, and I imagine that I'm quite close to my time now. The interesting thing about video decoding, or the kind of video encoding and decoding, is that we basically load this video file, we process encoded packets. There could be like 100,000 of them into RGB frames. A packet does not necessarily correspond to a frame. A packet can correspond to part of a frame. It can correspond to a lot of a frame. It can correspond to a number of different things, but we process n number of packets into m number of frames. Once we have our RGB frames, then we do the whole run through inference step and then get our results back. It returns a bounding box, of course. Once we want to re-encode our video, this is where things get a little bit tricky. And this is one of the caveats that I have at the moment with the current implementation. I spent probably 3 weeks in the evenings, also between trying to spend a little bit of time with girlfriend and moving to France, trying to properly re-encode the video. And I have gotten it to re-encode. However, I have not gotten it to re-encode to the original file size. So with video, there's basically encoded video rather. There's basically these concepts of iframes and bframes. Completely forgotten which one is which, but one of them, I think it's iframes, are the frames that include a full frame information. So RGB pixels values for every single one, for every single pixel, right? Full like reference image. And then the bframes, and I could have gotten this switched up, are the frames that are just inferred from the previous frame and some motion information. Okay, this doesn't change. These pixels, so this area doesn't change. These pixels, these ones do. And that's actually how we get efficient video instead of saving every single full frame to disk, right? It was surprisingly difficult to get any of that working. And I tried a number of different methods. So this is something that I still need to implement properly. So in its current state, it outputs videos larger than I would like, but it is a work in progress thing that I am actively working on. I figured get a accurate result, or get a result first with respect to actually re-encoding video, and then let's figure out how to properly re-encode video. Yeah, I was using FFmpeg version 4.4.2, and under the hood, I was using the NVEC encoder. So I have a 3070, an NVIDIA 3070 in my laptop, and so I was using the NVEC encoder of FFmpeg to do the encoding, which means that at least while the neural net wasn't doing inference on the GPU, the actual video encoding was. And that was actually very easy to set up. Learnings, basically what I said about broadcasting of arrays, very silly. iframe versus bframe and trying to re-encode packets properly. And the issue was a timestamp issue. There's a presentation and a decoding timestamp, and those didn't match when I was trying to re-encode the video back into a normal video container, a video file, using NVIDIA NVEC codec, encoder, decoder, as well as I need to basically upgrade to the latest version of FFmpeg. Yeah, so this is basically what I'm focusing on at the moment. Improve re-encoding, move to latest version, profile performance and improve, because I'm sure that there's going to be tons of areas in which I can improve performance. There's also a little bit of interface stuff that I'd like to do between the actual WASM SDK that I've written and the video plugin. And I want to finish Dockerizing it properly, such that other people can use it. So Dockerizing it not such that we run WasmEdge on Docker, because that kind of feels like it's defeating the whole purpose, but rather such that other developers can just say, okay, one click, I want to actually run this on my machine, or at least see the setup such that I have the correct libraries on my machine, at least for Linux boxes, people with Mac. Yeah, I don't have a Mac, so if someone wants to buy me a Mac, let me know. Yeah, so future work is then going to be this better interface for passing types. I'd like to also write a WebRTC plugin for streaming video. How that happens, I'm not entirely sure. I think it would be quite interesting. It would have to be a plugin kind of like the same vein of the video plugin that I have. And then we just need some sort of asynchronous interface between the WASM application and the WebRTC plugin, which shouldn't be so hard. Maybe it should be like a poll-based interface. I've thought about it a little bit, but I haven't actually had any time to put anything into practice. And then maybe just do a design review over the entire system. So that is my talk. Thank you very much for sitting here for probably much longer than you guys would have liked to hear me speak. Yeah, are there any questions?
Well, thank you so much, Charles. This is fascinating. That's although I'm involved with the project from early on, but it's nice to see so much work has been done. So in the interest of time, I just have one quick question, and we can have some more Q&A at the end. That's so. When you do this, what's the performance look like? So how much time does it take to detect one picture or one frame in a video?
Sure, that's a great question. Will I be brave and should we just test it right now? Let me quickly see. I think I can just quickly run this and share my screen again. Let me see if I can copy and paste this command and it works first time, then I'll tell you. Okay, the copy and paste command works first time. So let me share my screen again and we can see. Bear in mind, is this the correct screen? Is this the correct screen? This is the correct screen. Sorry, I have multiple monitors. So let's see, that's the opposite direction. So let's also use that. So I'm going to just run with one interesting thing that needs to be remembered as well is once you've actually created the WASM, you need to then optimize it as well. So there's a step here in the README that says cool use, I think it's WasmEdge compile, and it basically outputs a compiled version or an optimized version of the WASM. So I'm running with that, and then I'm running it on a busy street. Let's actually do a time for that. So this specific image takes 0.7 seconds, a little bit less, and we can see maybe the size of this image. I'm not sure which image I used, called busy street, and it's inside WASM RS, example inputs, busy street. So this should be like an embarrassingly small image. So it's not a very high resolution image. In terms of video, I need to fix it before answering the question. I know it is above a frame a second, but
Okay.
I know it is well above a frame a second, but I don't think it's real time yet. Once we get GPU enabled, potentially real time, but that's going to depend very much on the video, because obviously if you throw an 8K video at like an old CPU, it's going to depend on the video and the hardware, because if you throw like an 8K video at an old CPU or GPU, then it's not going to be real time. But if you throw it at some crazy NVIDIA Jetson, then probably real time. I don't know, depends on the workload, I guess. But it's not like it takes like 6 years to do inference, which is good.
That's excellent. So the demo you have just shown is running on CPU. Is that correct, or on GPU?
Yeah, 100%. This is running on CPU.
Okay, that's very interesting. We look forward to more work on this. So
Yeah, 100%.
yeah, thank you, Charles. Yeah, we're very impressed. So
It's a pleasure.
yeah, so let's move on to the last talk. So our very own Vincent gonna talk about another approach to integrate a GPU access and WASI-NN into the container environment. I think would be a really nice supplement to what Akihiro has done, and also I think maybe useful for Charles as well. Because that allows the whole thing to run in a content I wouldn't say in the regular container, in an environment that's more like Kubernetes. So Vincent, I'll let you talk, so that I don't mess it up.
Okay. Everyone can hear my voice. Right? You hear my voice.
Yes, I can hear your voice. Yes.
Okay. Wait a minute. I share my screen.
All right. Yeah. I see it. Yeah.
Today I'll share how to run our WASI application inside a container and the SS GPU device. Actually, the document published this week, and this is a new approach. So the idea is come from 2 years ago. Yes. I see Docker website share the article talk about how to access the NVIDIA device using container device interface. There are different with traditional way. In traditional way, usually the container user use the GPU device in running their image with NVIDIA on top. Now, in this case, we're not compatible with most application. So, because we saw an article talk about the approach, so we quickly do some testing and update our document in here. Everyone can see my terminal.
Yes, I can see it.
Okay, okay. So I will follow document, introduce our steps, step by step. Actually, the document will full cover for demo today. So if anyone want to produce our demo after community meeting, you can check the tutorial. Okay. First, before we start, we need a GPU device. And my research, currently, I only see NVIDIA support. So I not guarantee other hardware can support container device interface. So we should use the NVIDIA vertical. So you should install GPU driver and NVIDIA container toolkit on the host. And Docker version has minimum requirement. Desktop version is Docker engine version. So if I host Docker version, here. So if you install NVIDIA driver has any trouble, you can check this document. Talk about how to install pure chain on your host. And here we just check that your driver is okay. So it's my I will also check my toolkit. If your Docker version is beyond this version, so you can install next version on your host. Now next step is talk about how to relate the container device interface spec. This is rely on NVIDIA tool chain. So I will show you how I remove first. So and I will generate this. If we generate down, if I check the list, it will show you the device. And after you enable your container device list, you need to also enable it inside Docker. So by Docker topic here, I need to enable container device interface and device test. After it's done, you can check your environment itself okay with Ubuntu image. Next step, where I want to make sure our WasmEdge runtime is in 0 and enable WasmEdge config. And because I already built this before, so I can my passive here. I already built before, and I already update it in my Docker config inside. And here I will download a plugin to my host. If your host detect your NVIDIA device, you will install a GL plugin with good postfix and make sure all your dependency is good in your host. Okay. If you miss some dependency, you will see the library missing here. So before you run a demo, you need to make sure your host library is already installed. And in that stage, I will demo how to run our WhatsApp application, Llama inference application. And the download model, I will download in my step. Here, the next step, I will show you how to run the application. The first, I will binding our plugin into a container environment. And I also binding the dependency library into container environment here. And this passive is binding our inference model file. So I specify here, and I give two environment variable, tell our WasmEdge runtime to know where is the plugin test, and our inference model below parameter. So if you set it down, I can run this. inside. Okay. This is our Llama CPP file detail our GPU device and the network package. So okay, this is my prepared sharing. Yeah, I will show. Okay, secure one. Michael.
Yeah,
Yeah.
thank you. Yeah, that's very, it's great to see that, and I think that's it works on different level than Akihiro's earlier demonstration. That's so in this demonstration we are not trying to go through the gRPC port, but to have the media driver exposed and available as if they are on the host machine that inside the container environment, and make it available to the WASM application that's running inside it. So I thought that's so. They both have different uses, so I think that's yeah, it's great to see that there are different ways to do this now. That's we'd hope to that's to get to the point where we we can get some of those into production use. That's in the near future. Yes, thank you, Vincent. Yeah. So I know we are running a little late on time. Let's see if we can take one or two questions. So okay, so had I mentioned the C-RON upstream? Okay, C-RON. So C-RON merged our request so that I guess you don't need second state C-RON anymore. So you can just use regular C-RON. That's excellent. We should talk about this today. So yeah, we're running a little bit late. I think we are about 10 minutes over the time now. I know people have other things that they have other engagement. So that's so if you have questions that you can ask right now, but if not, I think we can finish this meeting and we can move the discussion and the conversation to GitHub and to our mailing list, and also our Twitter account. So all right, okay, all right. Thank you, everybody. Yeah, thanks, Charles, thanks Winston, thanks Akihiro.
Thanks everyone. Cheers. Bye.
Thanks. Bye bye.
Thank you. Bye.